Welcome to the Unit 5 of the course Remote Update of Programs and Functionalities. The title of this unit is Programming of Full Operation. In this unit, we will have a look at how an algorithm for performing a control scenario of the faster conveyor station will be programmed. Learning outcomes. By the end of this lesson, the learners will understand how an algorithm for full operation of the faster conveyor station is designed, programmed, and how it works in practice. Before we go ahead to the programming, let us quickly review what the faster conveyor station consists of. On the sensor side, we have the optical sensor on the left-hand side. This sensor detects any object, plastic or metallic, passing by. On the right is the proximity sensor, which only detects metallic objects. On the actuator side, we have the motor on the left-hand side. The motor is driving the conveyor belt and its direction can be reversed. On the right-hand side, we have the barrier. If the barrier is closed, the object on the conveyor belt is diverted. The presented algorithm will control the following operation scenario of the faster conveyor belt station. All objects that pass through the system are counted. Plastic objects are passed through for further processing. Metallic objects are sorted out with the help of the barrier. Before implementing the algorithm, we have modeled it with the help of a state transition diagram. Based on this state transition diagram, I will also explain how the algorithm works. At the beginning of the operation, the conveyor belt motor is started. Afterwards, the system waits for the first object to appear on the belt. Presence of an object on the belt is first observed by the optical sensor. If this is the case, the object counter is incremented. If, afterwards, the proximity sensor detects an object, this means that this object is metallic. In this case, the counter of metallic objects is increased and the barrier is closed for 1.5 seconds in order to divert the object. If no metallic object is detected 3 seconds after detecting a new object, it is considered that this new object is a plastic one. Therefore, the plastic object counter is increased. Let us proceed now to the implementation of the algorithm of full operation in B&R environment. First, we have defined all the variables. In the global variables section, we have defined the variables that will map the inputs and outputs of the controller, such as the barrier, the motor, optical and proximity sensor, and the reverse control signal. Let us see how the mapping is done. The variable motor is mapped to the digital output 3, as this is the PLC output where the corresponding wire for motor control is connected. The same goes for the variables barrier and reverse. The variables representing the input signals, namely proximity sensor and optical sensor, are also mapped to the corresponding digital inputs of the PLC, in this case to digital input 5 and digital input 6. Local variables of the algorithm, such as counters, timers, and variables for storing the counter values, are defined as local variables of the program. Now we can proceed to the programming part. At startup, every PLC program executes the code in the program init section once. This is where all the device and variable initializations are done. As we know from previous lectures about programming logic controllers, a PLC spends most of its uptime in cyclic execution, where the algorithm core is executed. In our case, we have some counters connected to the input signals, timers, and some further logic. All in all, the algorithm described in state transition diagram of the previous slide is implemented here. Before shutdown, the PLC executes the code in the exit section, but in our case, no actions are necessary here. So, let us observe the algorithm in operation. First, we will try out the plastic object. The object is detected, and the motor is started, and the plastic object is passed through. We can also observe that here the corresponding counter of plastic object is incremented. Let's do that again to see it again. Let's try now with the metallic object. The metallic object gets diverted, and also the corresponding metal object counter is incremented. Next, we will observe the full operation of the control algorithm implemented with the backup control system. Again, we start developing the algorithm by first defining the variables. First, if we have a look at the var section, where the local variables such as counters, timers, and some other auxiliary variables are defined. Then in the second category, in the input variables, as the name says, the inputs are defined. So in our case, this is the optical sensor and the proximity sensor. And the third category are the output variables. In our case, we will have a variable that controls the motor and another variable that controls the barrier. Let us have a look where the mapping of the variables from the algorithm to the concrete input-output channels is made. So if we observe this in the left-hand side of the screen, we have an I/O category where the devices are edited. So, for example, if you go to this device here, we have on channel 1 the link to the variable proximity sensor in the program. On channel 2, we have the link to the optical sensor, and on the other hand, we here on this device, we have the output variables mapped to the actual outputs. So here we have the barrier, and here we have the motor. If we have a look at the program code on the right-hand side here, so we have programmed this algorithm in structured text. Both B&R and backoff stick to the IEC 611313 standard, so the syntax for its structured text programs is the same, and thanks to that we were able to use the same code here as we have used in the B&R system. So, now it's time to see the backoff controller in action. We start with the plastic object. The plastic object passes through and proceeds to the further process. And let's try with the metallic object. The metallic object gets sorted out by the action of the barrier. If you have carefully observed, you have seen that the corresponding counters have been incremented. So let's do that again. Let's try to count the metallic object. Now we have 9, before we had 8. So let's do the same with the plastic object. So we incremented from 18 to 19 objects. Before the end of this unit, let us have a look at an interesting snippet of code that is counting the plastic objects. So, when an object enters the conveyor belt, it is detected by the optical sensor. However, at this time, we do not know whether this object is a plastic one or a metallic one. We only know a couple of seconds later 2 or 3 seconds later, when the object reaches the secondary, the proximity sensor. So if this proximity sensor detects that this object is a metallic one, then we increase the metallic object counter. On the other hand, if this, after 3 seconds after the object has entered the conveyor belt, the proximity sensor does not detect any object, then this object must be a plastic one. This video has received funding from the European Union's Erasmus Plus Cooperation Partnership in Vocational Education and Training Program. Thank you.